Hi, everybody. So last video for the assignments. Hopefully you guys are feeling better about the semester. I know we went over a lot very quickly. If I had a choice, this would have been, instead of the abbreviated summer session, we would have just used both halves of the summer to teach this entire class because it can be a lot. But I'm sure hopefully you guys learned something. So we're going to go over the fifth and last assignment. Hopefully you guys have been understanding this stuff, and hopefully you're happy with the points you've earned so far. Once again, if you have any questions about this class, feel free to email me, contact me through Slack, and I'm more than happy to help. So this is the last one, and we're looking at linear and angular kinetics. There's going to be a whole bunch of math for this one. We took a break from doing all the calculation stuff, but now we're back to it. Remember that all units should be in metric unless otherwise stated. So we're meters per second, meters, watts, joules, all that stuff. Remember to show your work. Put a box around your final answer, and you can either use the equation editor or, once again, write this all out on scrap paper and take pictures and send me the pictures. One thing I always ask, if you take a picture, make sure that I can read it. If it's a messy picture that's really blurry, I can't see that on my computer screen, so I can't really grade it. So you'll get what I can see. So just do your best if you're taking a picture. So once again, I'm not going to solve all of these for you guys. I'm just going to kind of give some guiding hints. So let's look at the first question. Mac is 185 pounds and moves from the 400 meter mark to the 750 meter mark in 15 seconds. What is Mac's linear momentum? So we've gone over momentum already. And once again, I suggest pull out one of the equation cheat sheets that are available on Canvas. I think the ones for exams 2 or 3 should have this stuff. But we know that momentum is equal to mass times velocity. I gave you mass, 185 pounds. And I gave you velocity. But you have to calculate. I gave you the numbers for velocity. So you have to remember how to calculate velocity. And I gave it to you in pounds and this in meters. So you'll have to do conversions because remember, we're using metric. So let's go on to the next one here. Dennis kicks a soccer ball with 65 newtons of force at a 37-degree angle from the time point of 0.4 seconds to 1.3 seconds. What are the vertical and horizontal force values? So we went over this, but this is basically our trig once again. Hopefully you've gotten used to solving the triangle. So once again, helps to draw this stuff out and submit it with your work. I like to see your thought process as you go through this stuff. But instead of writing, the opposite, hypotenuse, adjacent stuff, all this stuff, I like to, when I'm solving this stuff, I like to give them different names. So I'm going to say this vertical component here is f of y. Our horizontal component here is f of x, and I'll just say hypotenuse is fr for resultant, because why not? So I'm asking you to calculate f of y and f of x. So this is, once again, our trigonomic sort of thing. We have to figure out our trigonomic functions. So if you're calculating the opposite side and you have f of r is going to be our 65 newtons of force, at a 37-degree angle. Okay. So you have to tell me, oh, I'm sorry, it's going to be your 65 newtons of force is going to be your F of R, and your 37 degrees is going to be your theta. So you have to figure out, well, should I use sine, cosine, or tangent for F of X and F of Y? And then have how to rework those functions. And then just calculate them out. Remember, 3 significant figures, leading zeros and ones don't count. And show me your work. For your next part here is graph the impulse for both the horizontal and vertical force values. So when we're looking at impulse during the lecture, we know impulse is force over time. So when you're going to graph this, I'll do one here. On our x-axis is time, and on our y-axis is force. So you're going to show me, and it helps to put in your units here. You're basically going to give me a graph. This doesn't have to be absolutely perfect, but as long as I can look at your graph and understand the point you're trying to convey. Is what you're really saying is you're graphing the horizontal and vertical forces. Well, whichever one of those is the largest value should have more area under the curve. So I'm not going to do the math for you, but let's say that the horizontal force was greater than the vertical force. So I'll draw the vertical force. I'll use blue to draw the vertical force. Use this again, go back here. Okay. And we're going to say that's smaller than the horizontal force. I haven't calculated, but we're just pretending. It's going to be a slope like this. Okay. Now let's say we want to graph the horizontal force. And we said it's bigger than, oh, hold on. One last thing just to make it a little bit clearer is, so this right here for the vertical force is the area under the curve, right around here, array for it. And we're going to say the horizontal force, it was bigger, so it's going to have more area under the curve here. So it's going to be all of this stuff. Okay. Once again, not asking for it to be perfect and to scale and you to break out a CAD program or something like that. Just do your best. And as long as I can understand what you're getting at, you'll get your points. So let's go to number 3. Charlie weighs 513 newtons and runs up a flight of 80 stairs with a rise height for each stair of 12 centimeters and does this in 32 seconds. What is the mechanical work and power in the vertical plane? I shouldn't have to mention any more than this, then you already did a lab that answers this question. This should be a fairly easy one. So number 4, D drops a 5.7 pound ball from the height of 9.2 feet. After hitting the ground, it then rolls 6.3 meters in 4.6 seconds. So my first question to you, what is the ball's potential energy before it is dropped? And use the positive value of gravitational acceleration, which once again is 9.81 meters per second squared. So once again, if you have brought your cheat sheet, which more than welcome to use, you know that potential energy is mass times gravity times height. Okay, and remember, this is in metric. So I gave you pounds, I gave you feet. Probably convert those before you start solving this stuff. You're gonna get wacky numbers. And then for the next question, what is the kinetic energy once it hits the ground and starts rolling? Remember, potential energy is the energy of position. Kinetic energy is the energy of motion, and it has a different equation. It is kinetic energy, and these are all measured in joules, remember that. Kinetic energy is equal to 1/2 I don't know why this thing doesn't work. 1/2 mass times velocity squared. Okay, so you've got a little bit of work to do here. First, you should have already calculated your mass here, and I gave you it to meters and seconds here. So you've got mass, but you don't have velocity, so you'll have to calculate velocity. And then just remember your orders of operation for this equation. Stuff. All my chicken scratches. And then last question, number 5. Liam is an 94-kilogram diver who leaps off of the diving board with an angular momentum of 26 kilogram meters squared per second and curls into a ball to rotate. This is your position A. The radius of gyration when in the ball is 0.26 meters. I'm looking at a whole bunch of typos here that will be fixed by the time you're looking at this video. Liam then fully extends into a headfirst diving position, position B, where the radius of rotation is 1.84 meters. The time from position A to position B occurs in 0.87 seconds. You do not need to convert radians to meters here. And it shouldn't say Puma, it should say Liam. Like I said, I'm seeing a lot of typos here that'll be fixed by the time you see this video. So what is the angular velocity of position A? So we know that our angular velocity, and I'll just subscript it with an A to have, that is we can use an equation that will be on your cheat sheet. So for omega A, or angular acceleration A, we know that, excuse me, it is equal to H, which I'll let you determine what H is, times mass times K, our radius of gyration, squared. And I'll put 1 here for the first radius of gyration. There is an equation on the cheat sheet that has something like this, but you'll have to derive it yourself. But it uses all of these variables here. There's an equation that has all these variables in it. You just have to derive it. So that's for position A. Then you'll do something similar for position B. And then finally, what is Liam's angular acceleration between the two positions? So you're looking at a change in angular velocity. So just like linear velocity, or just like linear acceleration, it's very similar. You're looking at a change. This would be for linear acceleration, change in velocity over change in time. For angular velocity, or for angular acceleration, change in angular velocity is this. Change in angular displacement over a change in time. And then you do not need to convert it to radians to meters, but if you want to, you can convert it there, but you don't necessarily need to. That is it for the assignments. That is it for this video. If you have any questions about the assignment, and it's not 3 in the morning when you're watching this trying to complete the assignment, feel free to email me or contact me through Slack. I hope these videos have helped, and goodbye.